Hello everyone, welcome back to Pooky Codes and to part 3 of Neural Networks Explained. So in this video, we are going to look at the XOR problem and we will see why it is unsolvable with our current neural network. So let's get started. So we have seen that the formula for multiple inputs is of the form y1 is equal to step of w1 x1 plus w2 x2 plus w3 x3 and so on up until wn xn, where n is the number of inputs. Then you add the bias, so plus b1. Or alternatively, in a more concise form, it's equal to y1 is equal to step of sigma I equal to 1 to n of wi xi, and then you add b1. So the sum from 1 to n of wi xi, that's what represents the sigma notation, and this is equal to, if you develop it, w1 x1 plus w2 x2 plus w3 x3. So in this video, I'm going to introduce you to the XOR gate and also to other gates. And basically, gates are just a fancy way that takes two inputs, 0, 1, and gives one input a 0 or a 1. And I'm going to use these gates to visualize neural networks. So let's start with the first gate, which is the AND gate. The AND gate is a gate that returns 1 when both of these inputs are 1. So for example, here, for 0 and 0, you get 0. For 0 and 1, you also get a 0 because both of them are not 1. For 1 and 0, you also get a 0 because both of them are not 1 yet. But when you have 1 and 1, it gives 1. So now we're going to derive a formula for it. And I'm pretty sure from now you're a pro at it. So the formula is actually going to be y1 is equal to step of x1 plus x2 minus 1.5. So why is that? This is because when you do 1 plus 0 here, you still want it to output 0. So you want the threshold to be bigger than its sum, 1. Yet, you also want its threshold to be smaller than when you do 1 plus 1, which is 2. So you want it to be bigger than 1 and smaller than 2. So I chose 1.5 because it's in the middle. So if I test it, I have when x1 is equal to 0, x2 equal 1, I have y1 is equal to step of 0 plus 1 minus 1.5, which gives me step of minus 0.5, and since minus 0.5 is smaller than 0, this means I have a 0. I also have x1 is equal to 1, x2 is equal to 1, this gives y1 is equal to step of 1 plus 1 minus 1.5, which gives us a step of 0.5. And since it's bigger than 0, this gives us 1. So now I'm going to plot the points in the truth table. So this is called the truth table. And what I'm going to do is that I'm going to plot the x1 on one axis, the axis of what's called the x-axis, and x2, I'm going to plot it on x2 axis. And I'm going to color the dots if it's 0 and if it's 1 with different colors. So this is what it looks like. So for 0, 0, 1, 0, and 0, 1, this gives me y1 is equal to 0. So the dark blue class. And then when it's 1 and 1, this is true, so it outputs 1. So the y1 is equal to 1. This gives the purplish color. So, as you can see, when we plot this, we see that this could actually be classified if we somehow draw a line. So for example, if we draw the line like this, and we said that everything above this line is of class 1, and then everything below this line is of class 0, we would see that for every input, it will work. So 1, 1, it is above the red line, so it can be of class 1. 0, 1, 0, 0, and 1, 0 is of class 0, and as you can see, it is below the red line. So we know that for step of x given a function step of x, we know that all x bigger than 0 would give 1. That's the definition of the function. And that all x smaller than 0 would give 0. Just a quick refresher, step of x gives 0 if it's smaller than 0, if x is smaller than 0, and gives a 1 if x is bigger than 0. And we'll just say that when it's equal to 0, it's a 1. Alright, so we just need to find when x is equal to 0 in our neural network to find the boundary, because as soon as you move from that boundary, on top it's either going to be all zeros or it's going to be all ones, and then below it's either going to be all zeros or it's going to be all ones. So we have y1 is equal to step of x1 plus x2 minus 1.5, which gives us, if you develop it, we want to find it's 0, so x1 plus x2 minus 1.5 is equal to 0, and you solve it, move 1.5 to the right, and then you just make it of the form x2 is equal to something plus something. So x2 is equal to minus x1 plus 1.5, because this gives us a line where the x-axis is x1 and the y-axis is x2. So if you plot this line, we see that this is my 2 points of reference, these two, and I use these to just draw the line, and it is red. So as you can see, everything that's below the red line is of class dark blue, which is of class 0, and then everything above is of class 1, so the purplish blue. So as a conclusion, the neural networks of the form y1 is equal to step of w1 x1 plus w2 x2 and yada 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 plus b1 can be visualized as a line that acts as a boundary, and at all points on one side of the line is going to be of the same class, so all zeros or all ones, and on the other side it's going to be all zeros or all ones, because on the line, that is when step of x, for step of x is equal to 0. So as soon as you just move from on top or you move to the bottom, it's going to give a different class. So I'm now going to proceed with another example, the NAND gate. And we will see that it is actually the opposite of AND. So the AND gate was that it will give a 1 when both inputs are true, and the NAND gate is that it's always true except when both inputs are true. So as you can see, it's the negation of everything. So we have then y1 is equal to step of minus x1 plus x2 minus 1.5, and this is equal to step of minus x1 minus x2 plus 1.5. And the minus is here because I want to flip it. So before it was the AND gate, and now if I flip the step function, the labels are going to reverse. So basically, instead of going like this, it's going to go like this, and which is what we want. I want the 3 dots here to not be of class 0, but to be of class 1, so flip it, and the class that's up there, 1, 1, I want it to give a 0, so I flip it also. So let's calculate the boundary again. So we have yada yada yada, some math, some algebra, and we finally get as line x2 is equal to minus x1 plus 1.5, and that's the same formula, that's the same line. But the only thing that changed is that everything that's below the line is not of class 0, but of class 1, and everything that is above the line is actually of class 1. So the boundary line still remains, but the direction where the ones are and where the zeros are is different. We're now going to do the OR gate. So we have x1 and x2, and basically the OR gate gives true when at least one of the inputs are true. So when x1 or x2 is true, y1 is true. So to make a formula for it, we can see that the threshold, we want it so that when 0 plus 0, which gives us 0, it has to be, the thresholds must be bigger than 0, But we also want it to become a class of 1 when you do 0 plus 1, for example, which is of 1. So the threshold must be between 0 and 1. So we'll say it's 0.5, and this gives us y1 is equal to step of x1 plus x2 minus 0.5. So let's test it again. x1 equals 0, x2 equals 0. We have y1 equals step of 0 plus 0 minus 0.5, which gives us step of minus 0.5, which is 0. You have x1 equal 1, x2 equals 0. We then have y1 is equal to step of 1 plus 0 minus 0.5, which is equal to step of 0.5, which is equal to 1. So now we're just going to calculate its boundary. So we're going to take the line, the input that's passed to step, and say x1 plus x2 minus 0.5 is equal to 0 to find where the step function is going to have as input 0, and then say just calculate it, and we'll have x2 is actually equal to minus x1 plus 0.5. And if you plot it, we'll see that it gives us a red line like this, and that everything above this red line is of class 1, and that everything below is of class 0. Okay, now it's good. So we're now going to do the final example, which is the XOR gate. And we'll see that it's a special kind of gate. It's kind of like an OR gate, but when both inputs are true, it's going to be false. So in other words, the XOR gate, which stands for exclusive OR, is true when only one of the inputs is true. So if you plot it, we'll see that this gives us two dark blue, so two class zeros, 0, 0 and 1, 1, and two of class 1, so 0, 1 and 1, 0. And so now I can challenge you to find a boundary that can split the two of them. And you'll see that it's actually impossible. If you guys can do it, you guys are a fraud. I don't know how you do it. You're just lying. I won't believe you. So as the conclusion, XOR is impossible to separate with a line. So XOR is not linearly separable. So how do we still solve this with neural networks? And this is going to be the next topic, where we will create a neural network that can solve the XOR problem, and we must use an idea called multiple layers. So enjoy. Thank you guys for watching. So if you like this content, like, subscribe, and all that good stuff. And in the next topic, we're going to look at multiple layers, and we are now going to approach the real neural networks and deep learning. So stay tuned.